Good evening. Myself Shubh of Group 322. My first topic is game models and information aspect of self-organization. The Egan model theory addresses the problem of how order and information emerge from chaos. The process occurs in an open, far from equilibrium, autocratic system. The theory overcomes the apparent improbability of self-organization without contradicting physical law. To illustrate this idea, various game models are used. First is Heron's Fest game. Black and white pieces on chessboard randomly switch colors based on dice roll, leading to equilibrium, while fluctuations self-correct. This model system near equilibrium. Unstable distribution game. Pieces are replaced with others of the same color, leading to dominance by one color due to initial random deviation. This simulates the amplification of chance event without selective advantage. Random walk game. Coin toss determine color switches, creating oscillation between extremes. This represents behavior between stable and unstable systems. Egan's beat game incorporates birth and death phase of simulate Darwin evolution. Selective advantage molded as probabilities of beat duplication causes certain types, e.g. blue beats, to dominate over time. Introducing mutation such as error to reproduction shows a threshold where excessive color prevents the dominance of advantageous traits. The key takeaway is this displicative system, unlike those near equilibrium, can memorize random deviation, enabling the creation and retention of information. This self-organization allows systems to isolate existing information from noise and generate new information through mutation, driving irreversible evolution. My second topic is hypercycles. The Egan's hypercycle theory refines the model of molecular evolution by proposing that macromolecules do not directly self-reproduce but instead synthesize complementary chains, forming cycles of alternating plus and minus strands. These cycles are essential for evolution but face challenges such as mutation, accumulation, and instability and inability of long chain to evolve effectively due to error threshold. Key concept and features of hypercycles. Definition: hypercycles are autocratic system where information carriers, e.g. RNA cycles, guide their own replication and synthesis of enzymes that catalyze of the reproduction of subsequent carriers. Properties: enable state coexistence and mutual growth of all participants, allow competition within non-participants, replicating unit can grow or shrink for selective advantages from higher order network that stabilize component via non-linear oscillations. Selective advantages: stabilize phenotypic variation requires spatial separation to establish genotypic advantages, are resistant to replacement due to their dependence on population size. Emergence and evolution. The first hypercycle likely evolved stable molecules such as pre-tRNA with secondary and tertiary structure that provide resistance to hydrolysis and allowed cooperation between units. Functional relations between within hypercycles reduce competition among units and promote integration into effective system, preserving information and improving performances. Hypercycle laid the foundation of genetic code translation system and unified genetic coding. These systems evolved further through compartmentation and recombination. Challenges the origins of hypercycles. The generic code and translation system remains unexplained in the Eugene's theory. This structure likely did not arise by pure chance due to extremely low probabilities involved. A common comprehensive model needed to explain prebiotic and biological evolution, legitimate origin. My third topic is other models of prebiological evolution. Summary models of prebiological evolutions. Thermodynamic and mathematical model. Eugene's model focuses on selection of pre-tRNA with highest selective value mutational leading to increased order and represents the fluctuation decrease in entropy. The evolution of system is driven by mutation that destabilizes the system, potentially leading to rapid or gradual changes depending on mutational rate. Prebiological theory models evolution uses stability theory mutants erroneous copies of molecules. Many destabilize a system leading to new evolutionary regime. The system stability shift based on the interaction between existing and mutant substance. Autocatalysis and phase transitions. This mechanism describes how mutation can lead to the production of new polymer driving evolutionary shift. Cohen's model 1972 environmental periodicity. Evolution was influenced by periodic environmental change, for example temperature, humidity, which promoted the selective of stable molecules such as pre-tRNAs capable of replication. Prebiotic evolution occurred in mineral compartments, clay pores, and sea land boundary, with molecules undergoing cycles of dissolution and dying. Self-assembly played a key role leading to molecular complexities, the emergence of clarity in primitive membrane that eventually become independent of specific environments. Later evolutionary stages in Cohen's model, formation of molecular associates capable of replication despite error, emergence of protein as catalyst for nucleic acid synthesis via vice versa, leading to feedback loop and development of primitive enzyme membrane and a genetic code. Transition to DNA and the separation of replication enzyme synthesis mechanism. Evolution overcome limits in its generic information through sex and genetic recombination, facilitating the jump from prokaryotes to eukaryotes. Chernyshevskaya and Chernyshevsky model propose protein synthesis on polynucleotide molecules via mechanisms similar to hydrogenous catalysis, emphasizing the role of environmental periodicity. Evolution of transition mechanism occur prior to genetic code driven by complementary between nucleic acid and amino acids. Abling's and Feastel's model combines Eugene's theory with Operin's co-civitates, suggesting the early compartments acted as micro reactors. This supports catalytic cycle and molecular network, forming precursor of genetic code and early cells. Key takeaways: model illustrate the role of mutation, environmental influences, and self-assembly in prebiotic evolution. The compartmentation and the interaction of molecules with microreactor are central to early chemical evolution. While these models are theoretically incomplete, they demonstrate the potential of physics and mathematics to describe biological evolution and development. That's all for my topic.